Perfect. All right. My name is Kevin Tracy, and today I'm defending my thesis on differentiable convex modeling for robotic planning and control. So when I was in college, I was a mechanical engineering undergrad, and I had taken a few dynamics classes, and I was generally interested in aerospace. At the time, SpaceX had started to land the first stage of the Falcon rockets, both on land and on barges. And like many others, I saw this and I was like, this is the coolest thing in the world. I got to figure out how this works. And so when I talked to people who knew more about this than I did, they would say things like, oh, yeah, the control systems are just incredible on that rocket. And my understanding of control systems, intentionally in quotes here, was very limited. So I was super excited to finally take a controls class, figure out like just how to land a rocket, do something this crazy. Not gonna work. I then show up to my control systems class, and those of you who did a Mechie undergrad will know where this is going. And we didn't quite get to landing rockets. Instead, we were more focused on building and analyzing dynamical systems, and then synthesizing these controllers to stabilize or regulate these systems using these extremely archaic hand-drawn graphical techniques that were generated by these dudes. And this was cool, but the main assumption here is that I have a system with exactly one knob and one signal. And the assumption here is that if I turn the knob one way, the signal goes up. If I turn the knob the other way, the signal goes down. And so this kind of single input, single output control frame didn't really feel like it was too close to doing things like landing rockets. So it was cool and I liked it, but I kind of feel like there had to be a better way. So then I was introduced to a kind of new framework of thinking about all of these problems in grad school. And this was constrained optimization. And this is good for thinking about not just control problems, but every problem. And the way this works is I think about a vector x or a set of values x I want to minimize. I want to minimize some cost function f. And I have these constraints, g and h, that tell me which x's are actually okay for me to optimize over. And with this, we can think about how do we actually use this for a control problem? So what we want to do is we want to find some way to convert our control problem into a constrained optimization problem. So we need to take this abstract idea of what a trajectory is and make it something concrete that we can actually optimize over. So one way we can do this is we can think about a snapshot collection in time of a bunch of different time steps or knot points. And we'll think about the state of the rocket at each of these time steps. So in this case, the state will be the position and the velocity. And at these same time steps, I'll also have a thrust or my control. So what I've done here is I've taken this idea of a trajectory, and now it's a collection of vectors, a bunch of states and controls at a bunch of time steps. I can then form an optimal control problem where I use my constrained optimization framework. And I say I want to minimize over this trajectory, and I want to minimize some cost function. And in this cost function, I can encourage or discourage certain behaviors. And then I had these dynamics constraints, and this effectively says that the states and controls that I optimize over must actually obey the laws of physics. And then I have these general constraints. This is where I can encode anything else I want to. So I can have initial condition constraints, goal constraints, state action limits, things like that. And so how does this work for something like landing a rocket? And I think what's pretty amazing about this is that this is not that far from what actually happens. And it's certainly much closer than doing the hand-drawn, root locus Bode plots. So I set up a problem here where I want to minimize, say, the amount of fuel I want to use. I have a constraint that says I must obey the laws of physics. And then I have another general constraint that says make sure the rocket actually lands gently. And this can be something as simple as, when the rocket makes contact with the ground, the velocity must be below some threshold, and the legs will absorb whatever velocity I have left. Now for a more, robotics-focused example, here's Atlas doing a backflip. And again, this is not that far from what actually happens. You say in the cost function, do a flip. And then in the constraints, you say, make sure you always obey the laws of physics. And then in the general constraints, I can put a lot of stuff. I can say, don't hit anything, don't knee yourself in the forehead, don't hit your head on the diving board, like that kind of stuff. And the cool thing about this is that, as you can see from this backflip, there's probably a way, given enough, time and engineering, you could hand work a way for this Atlas to do a backflip. But there's something pretty amazing about setting up a problem itself, where the optimizer basically figures out what it has to do to make the flip possible. So for instance, it'll throw the arms back. You could hard code that, but in theory, if the optimizer has access to the dynamics, it'll figure out what behaviors it needs to actually make that happen. And also another fun note, if you look at this video, you see at the very end, there's some shaking just at the very end, which is, I guess a nod to the fact that the old school control stuff still is pretty important. So this seems really straightforward. And I feel like when I first got linked up with Zach and he was saying, this is the way to solve all of our control problems, it seemed really straightforward. I was like, here's this trajopt package, write down your dynamics, write down your constraints, and then pray. And that to me, I was like, that sounds good to me. So Zach got me all hyped on this, and the first problem I worked on was a low thrust orbit transfer. So we start on Earth, and I launched some rocket that has a satellite at the end of it. And the satellite is going to release itself into a geostationary transfer orbit. And at this point, the satellite has to use its own thrusters and its own power to basically move from a transfer orbit to a more permanent geostationary orbit. And this is actually not that straightforward. It takes a few months because the thrusters on the satellite are very efficient, but they're very weak. So I was like, all right, I'll do what Zach said. I'll just write this down as an optimization problem. I'll say I want to minimize the amount of fuel I use because fuel is important in space. I want to obey the laws of physics. I want to make sure that my rocket and my satellite obey the orbital mechanics present. I have to stay within my thrust limits because I have very weak thrusters. And then I want to make sure that by the end of the trajectory that I actually get to the desired orbit. So this was not at all as easy as Zach made it seem. This was like the most difficult problem I think I've probably worked on to date. It was 112 days and 90,000 knot points. And generally, when you're solving these optimal control problems, you want between 20 and 50 knot points. So 90,000 is pretty ridiculous. And I basically spent a few months doing a bunch of cost and constraint tuning, like tweaking things, trying to figure out how I could cheat a little bit. And this was so difficult that I basically gave up and then did nothing for a year. And then later in grad school, I kind of learned a little more about how these solvers work and what I actually needed to solve a problem of this scale. And then we finally solved it like a year and a half later with a custom solver. And this was a pretty interesting learning experience because it turns out it's a lot more difficult than just throw it to an optimizer and say, go solve this problem. There's a lot more handcrafted engineering that goes into it. The next thing I worked on that also reminded me just how hard some of this stuff is was contact implicit trajopt. So here I'm doing something very similar to optimal control, but now I'm minimizing over both the trajectory and a bunch of environmental contact forces. So relationships between the robot and the environment. As you see here, there's four relatively fun looking, what look like toy examples. This took months to get these four working. And we basically wrote a custom solver that could solve these specific problems. And it was absolutely not straightforward, and no off-the-shelf solver could solve these. So I think my kind of call to action for all of this is that I think that optimization is a crucial part of modern robotics and control, but I think it has to require less handholding. And I think that as amazing, as exciting as it is when it works well, sometimes it just doesn't work. And I think a lot of that has to do with how we frame these problems. So what makes a problem easier or harder to solve? So just at a very high level, if I take a constrained optimization problem, if any of the functions f, g, and h are non-convex, I have a non-convex optimization problem. And I want you to imagine something like this. This is, an extremely heinous cost landscape where there's clearly one global minima and a bunch of local minima everywhere. And the issue with this is that I have, first of all, no guarantees. I have no guarantee that I will find the global solution. I have no guarantee I'll find a local solution. And I can't even say that if there is a feasible solution, then I'm guaranteed to even find it. The second thing is that I have to be really clever with how I initialize these. I basically have to do a bunch of offline work to figure out what's the best place to start for these solvers, and then I can let it rip and try and find a solution. But the initialization is extremely important both for the quality of the solution and the time for the solution. And the last thing is that it can literally take forever. It can take 5 milliseconds, it can take 5 years. There's no way to know, given the problem itself in a general sense, how long it will take to solve one of these problems. Now, alternatively, we have, I guess, the light side of things. This is a convex optimization. So if the function f and h are convex and g is linear, this is a convex optimization problem. And I want you to think of this nice, beautiful bowl, which is a much more benign cost landscape than we saw earlier. And any local minima is a global minima here, and these problems are readily solvable. So I have some great guarantees. My first guarantee is that I am guaranteed to find the globally optimal solution. I don't have to start anywhere weird. I'm guaranteed to find it. If there is no even feasible solution, I can produce a certificate that says this problem is unsolvable. You will never solve it. I also don't have to initialize. There's some solvers where I can be clever and I can try and warm start this close to the solution, but by no means is this required to find a solution. And what I think is probably the most powerful is that I have a known solution time. And this kind of encompasses the first 2 points as well. They given a certain problem in scale, I know it'll take, for instance, between 5 and 10 iterations, and I can count on it taking that long every time I solve the problem. So I guess my kind of goal for all my research was I saw how amazing convex optimization was, and thought there has to be some way that we can really stretch convex optimization as far as we can and apply it to as many problems, even if it's potentially suboptimal compared to the true non-convex problem. So with that, here are some projects that I've been lucky enough to work on throughout my PhD, all of which have involved this concept of convex optimization. And today I'm going to really focus on 3 different projects. So the first thing is collision detection. This is determining if 2 convex sets are in contact with one another. The second is model-based plugging or insertion of like power connectors, things like that. And the last is something we've been working on recently, which is the trajectory bundle method. So the first topic is collision detection. And what I'm looking at here is I have 2 convex sets. They can be fixed or they can be moving. And I want to figure out if they're in contact or if they will make contact. So to motivate this, I'll give a very simple example here. So I am a blue triangle. I want to make it to X marks the spot. And I have to shoot the gap through this wall, and there's a hole in the wall. And you'd think that, if we can solve all these problems that, modern robotics people can solve, it must be very easy to solve this one exactly. And the way you actually solve it is way hackier than you'd think. You basically decompose the environment into a bunch of spheres, and you decompose your robot itself into a bunch of spheres. And I write down all these constraints that it says that make sure none of these spheres touch. And sometimes this approximation of the geometry with spheres is actually okay, and sometimes it's terrible. And especially it's terrible if I want to really shoot this gap and it's close and it's tight, and I can't afford to over-approximate these objects, then I have to use lots and lots of spheres. But it's a nice constraint to write down, it's easy to understand, and we can differentiate through it. So what I'm doing here is I'm basically trying to formulate my collision avoidance motion planning problem as a constrained optimization problem where I'm minimizing over some trajectory. I have a cost function, I have my normal laws of physics, and then I have this, famously vague constraint of don't hit anything. I think a lot of people think that the constraint is as simple as just saying don't hit anything, but there's actually a lot more hand engineering that goes into this. So to be very specific about what we're looking for is that we want a smooth function, let's call it alpha, that is a function of the pose of object A and the pose of object B. I have to return basically plus or minus, is there a collision or is there no collision? But it's not good enough for me to give this binary 1 or 0. I need actually smooth information between these, and I can't have 0 derivative. And the reason why is because I need to know, am I really close to a collision? Am I far away from the collision? Am I like a little bit in contact, or am I like totally all over this thing? The next thing is when I say I want to differentiate through this, what are the actual derivatives I want? So very specifically, I want the gradients of this collision detection parameter with respect to the pose of both of the objects. So the first thing we look at is, I guess, the simplest form of collision detection, which is discrete. So what we're looking at is I have 2 objects, they're both convex, and they're frozen in time, they're not moving. I want to figure out, are these 2 objects in collision? So how can we use convex optimization to find this? Well, one thing we could do is we could say, okay, let's find the closest point between these 2 shapes. And if this point is far away, like if there's any distance between these points, then we're not in contact. And this works totally fine when the objects are not in contact. However, as soon as they make contact, and I then try and solve that same problem of finding the closest points, I now have an infinite number of points. I have a set. And the issue is that all of the points in this set have a closest distance of 0. So my function that tells me how far apart these shapes are goes 0 as soon as I make contact with the shape. Now to solve this, we basically have to work around this individual formulations for in and out of contact. So let's think about a way we can potentially reason about this in a way that doesn't care if there's contact. So what we think about here is a uniform scaling that we apply to both of these shapes. So you imagine I take both shapes, I have this uniform scaling factor alpha. When alpha equals 0, it shrinks down to a point. When alpha equals 1, it's the size of the original shape. And as alpha gets larger and larger, it gets bigger and bigger. So what I'm solving for here is I want to find the minimum possible uniform scaling applied to these shapes that results in a collision between them. So in this case, these objects are not in collision. And that means that when I'm solving for the minimum scaling that makes a collision happen, I have to blow them up a little bit. I have to inflate them. And anytime I have to inflate the shapes a little bit or make them grow such that alpha is greater than 1, and then a contact happens, I know these objects are not in contact. So in this case, the minimum scaling is 1.2, which is greater than 1. So these objects are not in contact. Alternatively, if these things are in contact, and I set up the same problem, and I say I want to minimize the uniform scaling applied to these shapes that result in a contact, I can afford to shrink these things down to 0.6 of their original size, and I still have a contact at 0.6. So what that means is that if my minimum scaling that results in a collision is below 1, that means these objects must already be in contact. So this kind of gives way to decall, as I just described. So here I'm minimizing over two things. One is an intersection point. This is just a point in R3. And then I also have my uniform scaling factor alpha. And what I'm doing is I want to minimize this alpha subject to my intersection point is within both of these scaled shapes. And then what I write right here is me saying that I want to take the two shapes and scale them up and down by alpha. Now, the beautiful thing about this is that it is entirely agnostic to penetration. So if it's in or out of contact, it's the same formulation for both. This problem itself is a small convex optimization problem. It is guaranteed to always be feasible. So as long as your two objects have any semblance of volume in 3D or area in 2D, there will always be a solution no matter what. And there's no degenerate cases. So basically, this is a bulletproof way to solve for collision problems, given that the objects themselves have volume, which is a reasonable assumption. So then the last question is, okay, all I did here was work up a new way to solve a collision problem, but we haven't made this don't hit anything constraint any easier to put in our problems. So now the next question is, how can I differentiate through this to put it into one of these solvers? But now we're going to take a little bit of a detour and talk about differentiable optimization. So if I formulate a function as the output of an optimization problem, how can I differentiate through it? And there's a way to do this in a very clever way. So if I think about theta as being my problem parameters, and I have just a generic constrained optimization problem that is a function of theta. So for instance, for the collision problem, theta would contain the pose of both the objects. I can then write down the optimality conditions. So these are just our KKT conditions for this problem itself. Then if I look really closely at these first two, what I see is that I basically have an implicit function of the primal variable x, the dual variable lambda, and the problem parameters theta. So from here, I can go back to some old school calc, and I can say, okay, if I take a first order Taylor series of this implicit residual function right here, and I expand it about an approximate solution, I can then do some rearranging, and now I get the implicit function theorem. And so I now have a way with two derivatives in solving a linear system that I can produce effectively the sensitivities or the Jacobian of the primal and dual solution variables with respect to my problem parameters. Now, alternatively, if what I really want is just the gradient of our optimal objective value with respect to our problem parameters, I can actually cut one more corner. And here I can say that if I just take my Lagrangian at my solution, so the primal and dual solution, if I just take the gradient of that with respect to problem parameters, I recover this same gradient itself. And this is a very inexpensive and clever way to compute if this is the only gradient I care about. And the nice thing is that we now laid out two different ways that we can treat these optimization solvers as fully differentiable functions. And we can think about them as just as we would any other function in our stack. I can compute values and I can differentiate through them. Now, something interesting here is that, okay, I can form a derivative using the implicit function theorem, but how can I guarantee this derivative actually means anything or is smooth and is not just some weird subgradient? So let's take a look at everyone's favorite, non-smooth function, which is our ReLU function or our max element-wise. If I take the derivative of max x0 with respect to x, what I see is that I'm 0 while x is negative, and then as soon as x becomes positive, then I'm 1. And so my gradient effectively switches discontinuously between these things. So what we worked out was there's actually a pretty clever way that you can write this down as a QP. So I can say that, okay, I want to simply project x onto the positive orthant. Now, there's no reason you would ever solve for a ReLU using this, opposed to just using the max function. But let's for a second think about if we set up this QP. And I can then differentiate through that QP. And what I get is I have a way to kind of smooth these derivatives. So I can set with a tunable parameter, when I differentiate the QP and I form these derivatives, how much smoothing I want to apply to the derivatives. So here we see each of those lines is a different value for this smoothing parameter. So I can now customize when I solve a QP and I differentiate through it, I can effectively tune how smooth I want these derivatives to actually be. So with this, now that we have a smooth differentiable constraint that says don't hit anything, we can use it in a few fun examples. So the first one top left This is the piano movers problem. So here I'm taking a long rectangular object. I have to squeeze around some hallway. And I put constraints that, you can't hit any of the corners of the hall. On top right, I have a quad rotor going through a cluttered environment. Here I show just a whole bunch of convex shapes. These are all handled by the exact same framework. And I'm able to avoid all of them just with simple collision avoidance constraints. Bottom left, I have a cone that makes it through a little wall. So this is very similar to the first motivating example, but now it's in 3 dimensions. And on the bottom right, here is a contact physics simulation where I basically say, minimize over something that is going to give us the laws of physics, and then constrain it such that there's no penetration, and I recover accurate contact physics. So there's some issues with this. If I want to use discrete collision checking, and I want to use it for a robot that is moving with any sort of speed, I can run into some problems. So here, if I think about this trajectory in just 4 different points, if I check the collisions at all 4 of these points, I'm not in contact with the square. But if we look at this, obviously we're cutting that corner, so we will clip the square as you go between the second and third knot points. So this is not really going to solve this problem right here. So I have a few options. The first is I can just naively increase the number of knot points that I have. So I can say, okay, opposed to doing 4 knot points, let's do 10 or 40. Second option is I can add just a very large collision safety margin at the knot point and say, don't even come close to a collision, such that when I approximate this between time steps, that I'm not even going to come close to hitting this box. And the third method is I can effectively use a bunch of hacky heuristics like speed to adjust in real time what this margin or penalty is. So a very common one is I can say, okay, if you're moving very quickly, make the collision buffer that you give a little bit larger. That way the solver won't try and speed through certain obstacles. So this brings us to, I guess, is there a better way to think about what happens in between these 2 time steps? So this is a continuous collision detection. Now I have 2 shapes, and they're both still convex, but they're both moving. And I'm looking at them move between adjacent knot points. So each one is on this track, moving at time step k to time step k plus 1. And the question we're asking now is, will there be a collision? So now if we think about this in an optimization, uniform scaling-based framework, I now have 2 parameters. I have alpha that will inflate these things up and down, just like before. And then I now have this tau parameter. And tau is going to slide these objects on a track between time step k and time step k plus 1. So what the solver can do is the solver can wiggle both alpha and tau. They can figure out what do I need in the minimum alpha that results in a collision between these objects. And in this case, we can see that if I check the collisions at both knot points and just look at those knot points, they're not in collision, but obviously they're passing right through each other. So we should be able to identify some collision. So now we set up a slightly modified problem where I'm again minimizing over an intersection point and a scaling parameter, but I'm also minimizing over this time tau. And otherwise it's the exact same problem, same objective, everything, and I have all the same guarantees. So here's a pretty cool example, and obviously it's very simple, but it showcases exactly the problem with doing things with only discrete collisions. So on the left, we have what's called a tunneling example. So anyone who's played like an old video game where you can like run through a wall or you fall through like the floor on the map, this is often a result of this, is that I'll check collisions at discrete time steps, but I'm not really checking in between the time steps. So the solver can effectively just speed through the wall if it goes a little bit faster. Then on the right, we use our new formulation where we're considering both alpha and tau as we slide it on this track between the 2 time steps. And we see that basically we don't let the solver cheat. We don't let it try and speed through or tunnel through the walls themselves. Here's some, I guess, potentially representative examples of how you would use this. So on the left, we have 4 Francas doing a joint robotic welding task on some, bar sequence right here. And without this, they'll frequently nick corners, they'll pass through the bars themselves, or they'll hit each other. But I can directly reason about this full trajectory as it happens between the time steps and avoid all these collisions. And on the right, we have, similar to the quad rotor going through the cluttered environment, I now have a polytope going through a sea of other polytopes, but now everything is moving. And basically the only difference in this problem is now all of the collision constraints are continuous. And I'm basically representing what happens to these objects at both the adjacent time steps, not just at the knot points themselves. This brings us to our next project, which is model-based plugging. And here we see there's a Franca inserting a bunch of C13 connectors into a bunch of power outlets. And I think it's first important to motivate, I guess, why plugging is hard for humans. And I'd argue that actually is more challenging than it should be. So if I take USB, for instance, and I go plug it in, doesn't work, flip it, doesn't work. And then if you've seen this meme, I try a third time and then superposition, all of a sudden it works. And it's not really clear why. So I think it's important to think about like how humans actually reason about this and what does the human control stack look like. So at least for me, it starts with I do a little bit of wiggling. So I put the plug in, I do a quick little wiggle, I see how it feels. I then use how it feels to kind of build some mental model of what the actual force environment is like inside the plug. So am I stuck on a certain end? Is it like really loose on one side? And I then use this, and I use this model that I built up in my head to kind of finesse the plug-in with the least amount of resistance. So if you want to think about this in a control sense, I have a bunch of calibration moves. I have sysID, and then I have a control step. And it's important to know here that plugging is really hard to simulate, and it's hard to simulate accurately. And this is for a few reasons. The first is that these plugs themselves will have a bunch of slight deformations. They'll squeeze just a little bit when they get into the plug itself. It's actually a very precise fit. So for instance, if I take an HDMI cord and I miss by a little bit, it's never going to go in because I'm off by a fraction of a millimeter. And the second and third thing is that the hardware itself ages over time. So if I take one plug and I plug it in 100 times a day, it'll feel different by the end of the day than it did at the beginning. So normally what you do when you're doing sysID is I try to learn some physics model. I want to learn a discrete dynamic system that takes my states and controls at one time step and tells me what my state will be at the next time step. But really, I think there's actually an easier way to go about this problem, and that I don't want to learn a full physics model. I just want to learn a force torque sensor model. And so by this, I don't need the dynamics in my head. I just want to figure out some relationship between what I'm doing with my hands and the force and torque I feel on my hands. So I don't need to learn a simulation. I need to learn a simple relationship between my actions and what the sensor feels. So how can we do this? So let's start as simple as possible. Let's take a linear force model. So let's map our state and control to what we call a feature vector. So here we have some nonlinear function that takes an x and then a linear bu, and this produces some feature vector w. And I then say that I want to find some linear mapping that takes this feature vector w and maps it into the force torque value y. And this is what we call linear model learning. So I have some feature vector w as I described. I'm now solving this optimization problem. It looks at a sequence of a trajectory where I basically did some wiggling and I collected a bunch of force torque measurements. I want to fit this G such that I'm minimizing a little bit model error and a little bit some regularizer that says, the values of G should be something reasonable. And I use this to find online what a reasonable mapping G is that maps my feature vector to my force torque vector. Now, the cool thing about this is that this is a convex problem, but it's potentially really, really big. So if you imagine if I have a large feature vector or a large sensor space, or I'm doing this over 10,000 measurements, this problem can get very big very quickly. So to solve this, let's instead use the linear model learning algorithm that we introduced, which effectively uses a bunch of little tricks to treat this as a recursive least squares problem. And then we use a Kalman filter to solve this problem. So we think about G hat, this is our estimated linear mapping. This is what we're actually learning online. And if we treat each row of G with its own belief state, so it has a mean and a covariance, what we see is that given this specific problem structure, they all have the exact same covariance. And we can use this to have some sort of shared or global covariance. And then each mean mu is specific to the row itself. And the result is that since we're doing things in a Kalman filter, and this everything is still linear since the mapping between the feature vector and y is linear, what I get is I get global optimality without any need to do matrix conversions. And the beautiful thing about this is that if I can solve this thing for a globally optimal mapping, and I don't need to invert any matrices, this will run very well in a GPU since everything can be parallelized. So on the left, we see we run this for a bunch of different feature sizes and measurement sizes. We run this on a CPU, and we see about what we'd expect. This thing blows up with n squared. So if I have 10 times as many measurements, I have 100 times the compute. But then we see if I run the same algorithm on a GPU, I literally can do whatever size I want to, and the time, the wall clock time it takes to update this matrix G is the same for everything. And what's kind of crazy is that if I look at two models on the two different ends here, A and B, model B is 100 times the size of model A, but the wall clock time is the exact same. So now what we did is that we identified a way that we can do some calibration moves, we can do some sysID, and we can wiggle the robot, and we can run the linear model learning algorithm to learn what this force model is. So now that we have a force model, how can we actually guide the plug to a smooth insertion? So now since we have this linear model, which is very easy to work with, I can set up a convex controller where I say I basically want to minimize the force and torque on the plug itself. And then I'll add some term here that makes sure that my new U stays relatively close to my old U. So I don't want my controller to do any thrashing or anything. I then add a constraint to guarantee this. I say that, okay, I have some limits where I want U to stay within some semblance of close to U old. And I then run this online for a few systems. So here on the left, I have a plug that is slightly misaligned. And the instruction is just to just shove. And as we shove, we see these contact forces are relatively large and they're super misaligned. Now, alternatively, if we do a little bit of wiggling and we learn this mapping between what our control is and what the force torque on the plug is, we can learn this very quickly, and then we can use this linear mapping to effectively remove all of the unnecessary contact force on the plug itself. And this works both in sim and on hardware. It actually worked on hardware first. So here is, which is extremely unlikely, but is true. So here we have an example where we're doing a bunch of plugs, and each one feels very different just to a human. If I go plug things in, some are very stiff, some go a little bit deeper than others. And so what we do is that we go around and we wiggle on each plug, and we learn this like force torque mapping for each one. And then we can just guide these like perfect insertions for each of them. And this now brings me to, I guess, the most recent thing that we've been working on, which is the trajectory bundle method. So I think first it's important to kind of set the scene with like what's going on in the world of robotic simulation. What are the things that people are taking note of? So one thing is parallelism. There's been a huge effort in taking these simulators like NVIDIA's Isaac Sim, or more recently with Mojoko in JAX or MJX, and running these sims in a way that we can do thousands of parallel evaluations. So here we see a bunch of Francas doing a lot of things in parallel. We can do, Mojoko humanoids, we can do 4,000 all in parallel. And another thing that our lab has looked a little more closely at is how to actually differentiate through these simulations when we make and break contact in the environment. So contact is an inherently non-smooth behavior. And so there's some way that we can compute these derivatives through this non-smooth behavior using some numerical smoothing, and then use these smooth derivatives to do model-based control. Now, this is just like completely my opinion, but I would say the interest in parallelism is on the rise. I think people are realizing that this works extremely well, scales very well, and GPUs are only going to get better. So this is like something I think we should invest in. And as far as how to actually differentiate through these sims, this to me is a little more of an open question. It's not clear to me what the best way to compute these derivatives is. And it's also not clear once we have these derivatives, like what do we actually do with them that makes control better? So with this, let's try and think of the most basic problem we can solve, which is assume I had this black box simulator. This takes in a state and an action and gives me a state at the next time step. It's black box, so I can't differentiate it, but I can evaluate it in a massively parallel scale. So I can do, 100, 200, 4,000 parallel black box evaluations, and I can do that effectively for the same walk-off time. So the question is, if all I have is a black box simulator, can I still do like optimal control with a black box sim? So one way we could do this is with single shooting. This is probably the most, I guess, the simplest implementation of this, is I take my optimal control problem. And now I'm just going to optimize over my controls U, and then I recover my X's with a rollout. So I use whatever method I want to compute U's, and I do a rollout, a forward simulation, and I evaluate the cost, and I find some way to, in a clever fashion, improve on U. So a good example of a single shooting method is MPPI, or Model Predictive Path Integral Control. And what we're doing here is we're effectively adding noise to the nominal control policy, doing a bunch of parallel rollouts, and then we're using a weighted average based on the cost of each rollout to find a new control policy. And this has been super popular in the last few years, specifically in the last maybe 6 months, because people are finding that with these modern sims they can run in parallel, I can now do MPPI on a scale that was much more difficult even 5 years ago. But there's a hang up with this. So let's take a very simple example, which is a quad rotor that is being controlled at the rotor velocity level. So I effectively have 4 points of force control. And this is an open loop unstable system. I need clever control to keep the quad rotor flying. Otherwise, it'll just flip over and do weird stuff. So here I'm using MPPI in an entirely offline sense, so I can take all the time I want to. At each iteration of MPPI, I'm doing 1,000 parallel rollouts. And the situation here is that I start with some non-zero velocity and I tell the controller, bring me back to the red dot. And what we see is that after 100 iterations, it's falling to the floor, but it's not quite flipping yet. 200, it's a little bit better. It's kind of getting there, but still falling. And even after 3,000 iterations, right? So this is 3 million simulations later, and I still can't really recover any semblance of controllability here. And I think it's important to note like just how much compute is involved in all three of these scenarios, and we still can't stabilize this system. Now, alternatively, if we use LQR, which is every model-based person's dream for a controller, I basically compute the simplest possible control problem with one linearization, and I use a linear feedback policy, and I get this like beautiful, amazing, smooth, stabilizing control. And I think this kind of like illustrates the point that it's really important how we choose which method we use as a controller, because in this case, all it took was 2 derivatives, and we dramatically outperformed something that took 3 million simulation samples. So what are some things that we have to think about if we want to simulate our systems on a GPU? So the first thing is that I can do a simulation on a GPU. Let's say I'm doing some harmonic oscillator, and I can simulate this on a GPU in some amount of time. And generally, one simulation on a GPU will take between 5 and 100 times it would take on a CPU. But the nice thing about this is that I can effectively do a bunch of these things in parallel. So for the same speed it takes to do one simulation, I can do 4 for the same wall clock time. And I can keep blowing this up. I can do 4,000 simulations all in parallel, and it effectively takes the same wall clock time. So if I was doing single shooting, that means that each rollout is running on a relatively slow GPU single-threaded sim. But if I think about this in terms of multiple shooting, I can be a little more clever. So in multiple shooting, what I'm reasoning about is a bunch of different windows of the trajectory, and then I glue them together with these defects. So what I say is that I'm going to solve a problem that represents the trajectory in a bunch of these windows, and they must actually connect at convergence to reassemble into a real dynamically feasible solution. So now if you look at this, why does this help when we do things on a GPU? So in the first case, I'm doing just one full simulation, and it takes, say it takes 10 seconds. I can then now do 2 simulations, and I can do this in a multiple shooting framework where I basically chunk them up into 2 of these windows, and then I evaluate these windows in parallel. And what I see is that basically the more windows we have, the more speed we have. Now I do this for 4, and now the time it takes for me to evaluate my dynamics constraints is a quarter of the time as doing the full rollout. And I can keep playing this game, and I can keep increasing the number of knot points or windows that we have in our trajectory, and I can speed up the constraint evaluations. So the next question is, how can we actually approximate our dynamics without forming these derivatives? So what we showed in the quad rotor example was that having derivatives sometimes is like the ultimate cheat code. It gives us great control with very little compute. But if I can't compute these derivatives because our dynamics is a black box simulator, how can I actually approximate them? So normally what we do is if I want to approximate a function that is differentiable, look at a very simple 1D function here where y is equal to g of x. And I say I want to approximate this thing or linearize it around x bar. What I do is I simply take x bar and I evaluate g at x bar, and then the derivative of g with respect to x at x bar. And I use this to fit this affine approximation of this function that's relatively good around the linearization point, and then generally speaking gets worse the further we go. So here, if I kind of think about a completely different way to approximate these functions, let's look at the interpolation on affine functions themselves. So if I take an affine function here in gray, and I evaluate 2 different points, x1, y1, and then x2, y2, what you'll notice, and this is very easy to see in 1D, is that any linear interpolation between the first and second points is still on the function itself. So if I take this x1, y1 point, and I smoothly interpolate between x1 and x2 and y1 and y2, I can go back and forth. I will always be on the function itself. This is important because if I have an affine function and I have 2 values of this function that are true, and I linearly interpolate between them, I stay on the function itself. So I can be very general in the way I describe this. I can now have a interpolation vector alpha. So alpha is normalized in the sense that it sums to 1, and alpha is always positive. And what I say is that for some affine function f, if I take an interpolation of the inputs, this is equal to the interpolation of the outputs. So I can compute a bunch of affine samples through this affine function. And I can just arbitrarily interpolate between the inputs to find a new point. And the value of that point through the function is an interpolation with the same alpha vector on the outputs. So what we've done here is that we're effectively approximating globally exactly in the affine case without any derivatives. So how does this work for nonlinear functions or any function that is not affine? So here I have an input domain x, and I'm using this function g to map x's to y's. And what I see is I want to approximate this function in some neighborhood of x. So what I do is I compute a bunch of samples that are, close enough to where I want to approximate this. I then evaluate each of these samples through the function itself to compute the corresponding y's. And then we can think about kind of convex halls of the inputs and the outputs. So say I want to approximate this function on the domain that is in the convex hull of my sample points. And I have a bunch of corresponding outputs of these sample points and some convex hull there as well. What I can do is I can use this same approximation, but now it's only approximate, where before for affine functions, it's exact. Now I'm effectively saying that basically, if I interpolate the inputs, I approximately get the interpolation of the outputs. Now it's not exact because it's not affine, but as long as I'm sampling in a close enough region, it's approximate. And this gives us another clever way to approximate nonlinear functions with only taking a bunch of samples and without taking any of these derivatives. So some way we can think about this visually is that if I have a bullseye x and a bullseye on y, and I want to linearly interpolate between these x's, I can predict what the y is going to be as I move this thing around between the same interpolation alpha between these samples. So this now gives us a way to reason about this function in a way that's just a bunch of linear combinations of sample points, and there's no derivatives or differentiation required. And one important thing to note here is that this is not the same as us trying to approximate the derivative or anything. So if I take a Taylor series of this arbitrary nonlinear function, and I linearize this thing about x equals 1, y equals 1, what I get is I get this exact approximation at the linearization point. You see in the very center of this, my error is 0. And I'm comparing my approximation to the real function. So what I see is that, I'm exactly accurate right where I linearized. And then the further I get from where I linearized, generally I get less and less accurate. Now, if I use linear interpolation and I compute 4 function values at the 4 corners of this grid, and I use this trick to effectively interpolate the input-output values to predict what I think the output would be, what I see is that it's not necessarily better or worse than the Taylor series, but it is different. So it's important to know that what we are using here to approximate this function with sample points opposed to derivatives, we're not reconstructing the Taylor series. We're forming an entirely different approximation that is potentially better, potentially worse, but it's not us trying to get at a Taylor series. Now this leads us to the trajectory bundle method, which is relatively straightforward. The first thing we do is we take our current trajectory, or our initial guess. I'm going to sample, let's say, m trajectories that are in the neighborhood near the current iterate. And again, this approximation is more accurate the closer I am. So let's say I want to sample within some trust region where I actually want to evaluate my step. And then from here, I compute the function values for all these samples. This is my cost constraints and my simulation. I compute this for all these m samples. And I then approximate all these functions with linear interpolation. So I use the samples to assemble this linear interpolate in the same way I did earlier. And then from here, I can now form this convex approximation of the original problem. So before where I had nonlinear functions, non-convex functions, I basically have taken a few samples and rebuilt an approximation with linear interpolation, which gives us a nice convex problem. And I can iterate on this until I converge. So here's our, specification for how we want the problems to actually look like. And there's 3 main functions of interest. So the first is a cost residual function R. This takes our state and control, maps it to some vector R that we take the least square of, or we take the sum of squares of. Then we have our dynamics function. This is our black box simulator. And then we have a constraint function. And could be goal constraints, could be our keep out constraints, initial condition. They all go in the general constraints. And the assumption here is that I can evaluate all these functions in parallel at a very fast rate, but I have no way of differentiating any of these. So all 3 of these functions are black box to me as someone trying to make the solver. So let's take a look at a single window. So if I look at between T1 and T2, so just one chunk of the trajectory, and I focus on this of what the trajectory bundle method actually looks like for a single window, here's what I get. So I get, again, m samples around the iterate. So I take an x and a u, and I produce a bunch of these samples. And I stack them into these matrices WX and WU. Now, each column of these matrices is another evaluated sample. I then take all these samples and I run them through my three functions of interest. So my cost residual, my dynamics function, and my constraint function. And I evaluate this m times with each of the samples. And I stack them again into a new matrices, WR, WF, and WC. And now I have a collection of my inputs in X and U and my outputs in RF and C. Yeah, yeah, please.
The subscript is a timestamp of different sample events.
So it's not there's a little bit of abuse of notation here. So we're assuming one window right now. So we're just looking at one time step in the trajectory. And here the subscript is the sample number. Okay, yeah, so we're just looking at one window of this. I then am going to use the same trick where I interpolate the state and control with the same interpolant vector alpha. And then what I get is I get an approximation for what the output of these functions would be as a function of the interpolant vector alpha. So what I've done is I've effectively saying I take m samples of my X and U, I run them through all my functions, and I build these interpolants, and I can exactly approximate the inputs by just blending between the samples, and I can approximate the outputs by using that same blend on the outputs of the functions. And the cool thing about this is that everything so far that I've described is parallelizable. So when you compute the m samples within each bundle, I do that all in parallel. But also I can do this for each of the bundles also in parallel. And what this means is that I'm doing a bunch of function evaluations all in parallel simultaneously. And each of the dynamic simulations, they're all very short. And so what we get is that we get this resulting trajectory bundle subproblem. So here we have our cost residual function, R, is now replaced with this affine approximation of it using our interpolant vector alpha. I then have our dynamics constraints, and everywhere that we used to see our previous black box non-convex function has been replaced with this linear interpolation. So I've taken an arbitrarily non-differentiable non-convex problem. I've taken a bunch of samples, and I've replaced it with this locally approximate version where all the nonlinear functions are replaced with these interpolants. So here is everyone's favorite traject example to get things working. So here's a cart pull swing up. Start with the pull down, and we can strain it to be at the top at the very end. And this is a cool problem because it's relatively nonlinear. So to test like how well does your approximation method work. And then on the top, we see how the actual iterates of the solver itself converge on the solution. So we have configurations, velocities, force on the cart. This is our control. And then we have our constraint violation. So in this case, our constraint violation, this is our dynamics infeasibility or the defects between each of these windows in the trajectory. So it's not a real trajectory until this number is below some tolerance we have. In this case, it goes below 1e minus 4, and for our purposes, that is converged. What we see is that we get a classic swing up, everything looks good, and it takes about 35 iterations. We then revisit the quadrotor, which again, for MPPI with no derivatives, but an insane number of samples, had trouble effectively stabilizing this quadrotor about just an initial shove. And now I'm making it track like an elevated figure eight. And what we see is that the control itself looks great, looks smooth, looks very optimal. Then we see how this thing converges, and we get great constraint satisfaction. So our convergence on an optimal and feasible trajectory looks pretty good. And then it's just nice in general looking at how we initialize these variables and what they actually converge to. So for instance, for our control, we initialize with just noise about hover. And it's noise about hover for a little bit, and then it gets a little noisier, and then it converges on this beautiful, smooth, optimal trajectory. And what's nice about this is that everything here is entirely no derivative, like no models used in the sense of no A's and B's. And we're able to recover this beautiful optimal control looking performance. And then we mentioned that we have these arbitrary nonlinear constraints C, and this can include anything. And I made no assumption of differentiability of that as well. So here I use some collision keep out constraints. I say here's 3 convex obstacles, and I must keep a double integrator that starts at the top right and ends at the origin. And I must keep our robot, whatever it is, away from these obstacles. These constraints are all non-convex and non-differentiable in this case. And what I do is I use these samples to approximate the constraint function. And I get, again, great convergence in like less than 40 iterations. And again, I have control bounds on the control. So you can see that I've capped the acceleration between -3 and +3. So all these constraints that we have in this problem, they're all just natively handled by our evaluations and our constraint function itself. And with that, I like to say, they say it takes a village. This is said village. A lot of you guys are in this room. I have enjoyed, this PhD a lot. It's been like the most rewarding thing I've ever done in my life. And it would not have been possible without the help of everybody here. So if you see yourself, high five. Thank you. And with that, thank you, everybody.